We're all about clean energy, clean power, and looking at the global demand of energy over time. And we chose this path of advanced reactor design to be our part of that play.
This is EnergyCast, and I'm Jay Downhauer. Today we're talking about the next generation in nuclear fuel, ensuring a reliable carbon-free energy source for decades to come. During a recent presentation for E4 Carolinas, I showed a slide that broke down my episodes by energy topic, and nuclear was underrepresented. I'm going to make an effort to fix that, starting here. As today's guest explains, most commercial nuclear plants today use what's called an oxide fuel, usually uranium dioxide, in the form of pellets inside a metal tube or fuel rod. The rods make up an assembly and have to be swapped out every 18 to 24 months. In episode 33, we profiled a metal fuel technology with Lightbridge that's very promising for its efficiency and high heat tolerance. My guest today is developing a commercial-grade TRISO fuel, that's short for tri-structural isotropic, and is essentially a silicon carbide-coated uranium kernel embedded in graphite and packaged in a sphere that looks like a silver tennis ball. There's no metal involved, and that's what they say is key. In the case of Fukushima and 3 Mile Island 30 years ago, the reactors got in trouble when there was no water in the system. The fuel containing metal melted down. Now, heat generated from uranium can't melt graphite, so the heat will eventually dissipate. This technology also avoids water as an intermediary. The current generation of nuclear plants use water in contact with fuel to ferry heat around. In instances like Fukushima, where water couldn't be pumped around, the remaining water and water vapor was heated into free hydrogen and created an overpressurization event. Not good. My guest says they are using helium instead of water. Helium, unlike hydrogen, will never overpressurize and cause an explosion. Combining helium with a melt-proof design, my guest says they can ensure a safer nuclear energy future. My guest today is Darren Gale, Vice President of Commercial Operations for X Energy, a reactor and fuel development company based in Rockville, Maryland. X Energy was founded by Dr. Cam Ghaffarian in 2009, but Darren is based here in Charlotte, and I live there too, so I couldn't resist an opportunity to finally do an in-person interview after all these months. X Energy is exploring several business options with their TRISO fuel technology, including conventional nuclear fuel, a mobile option, solutions for space, and even small modular reactors. The afternoon we sat down was about a day after NuScale, who we've discussed on this program, finally received their design approval from the Nuclear Regulatory Commission. That should hopefully pave the way for companies like X Energy, with their own take on these smaller reactor designs, to get approval as well. I hope you enjoy my conversation with Darren Gale. We're here with Darren Gale, Vice President of Commercial Operations for X Energy. And Darren, you're the head of commercial operations, so I have to ask, what's commercial now with X Energy?
Yeah, that's a great question. We are a reactor development, fuel development company.
Yeah.
So we have been relying on the Department of Energy wanting to progress advanced reactors, and they are doing funding opportunities where they're helping companies to spend the money to get new designs developed, new reactors developed. So at this point in time, we are still in the development stage for commercial, but we're getting close. We've got fuel that we're near to being able to produce commercially. And then of course, we're looking to get up and going in this funding opportunity from DOE for an advanced reactor. So we're within a few years now of stepping into the big time with some commercial products.
Sure.
So.
The industry standard, whenever I do a nuclear episode, I always find that I have to do a lot of reading beforehand and also also consulting with a lot of coworkers who've spent time in the nuclear, but it's my understanding the industry standard is metal oxide fuel. I had a guest on Lightbridge who explained metal fuels and the benefits of there. Now, you're developing a TRISO fuel, so how does TRISO fit in with the metal oxides, which are kind of the standards right now is what most people are using, the metal fuels, which I think they're still working on getting certified for. Where does that land in the mix?
So the typical commercial light water reactor fuel is a uranium dioxide. So that's a ceramic pellet inside a metal tube, a fuel rod, they call it. That's the standard, has been the standard for decades. Most commercial operations are done with that. A metal fuel is where you infuse the uranium into a metal, and so you literally have a metal rod, whatever it might be. We have what is called a graphite pellet. It's a kernel embedded in a pellet. The difference here is that we're not having to use metal, and the melting point of metals, zirconiums and whatever, is such that you always have to worry about accidents. And so when there's a loss of coolant, the heat that is generated typically is higher than a melting point of a metal. Well, it so happens it isn't higher than the melting point of graphite. So by infusing this fuel into graphite and having the graphite contain the fuel, you essentially have a walkaway safe type of plant when you're using that type of fuel. Even when you lose the coolant, this essentially graphite tennis ball can just sit there and it's just going to dissipate the heat and not ever destroy or misshape that pellet, that fuel element, if you will. And so you can decide then what you want to do, but it's not going to cause any significant radiation releases in that sense. We have a small kernel that we make that is a silicon carbide coated uranium kernel, and then you embed that in a graphite tennis ball sized pebble.
Yeah, we've seen that tennis ball.
You've seen that, people holding that really shiny graphite tennis ball, if you will, and it just has thousands of these tiny kernels embedded in that graphite tennis ball. So that's and then so those tennis balls then are just fed through the reactor on a continuous basis. So you don't have to stop the XE100 reactor that we're developing for commercial use. It's a continuous refueling. So now where most commercial reactors will have to stop every 18 to 24 months, stop for about a month and not produce power because they're doing refueling and maintenance. Our reactor is not that way at all. It's a continuous refueling. There's just a flow of those tennis balls through the reactor. It can just continue to operate. Now you will still have to do some maintenance, so you'll stop for not nearly the amount of time that you would a conventional reactor.
The assemblies, right? The fuel assemblies, typical ones look like a cluster of very slender rods, slender bars, if you will. Help us understand if it's not in an arrangement that's like a standard fuel rod assembly. It's these large cue balls that are being fed around.
So helium is our coolant. That's the gas that is fed through the reactor, and that's what takes the heat generated from the fission reaction, right? Takes that and then removes the heat and takes it to a steam generator, another heat exchanger that then you transfer to a water that you turn to steam, and then that steam can be either used for process heat or it can be used for the typical turbine generator, right, to create electricity. Instead of water, we use helium. And then the pebbles are fed with a fuel handling system. So you have a tube system, if you will, taking the fuel through the reactor, will bring it then back out of the reactor, and then you do a test for each of the balls, each of the pebbles of what burn up or what use you've gotten out of that. And then you either put it back through the reactor or then take it out of service and put it into fuel storage.
How fast are they circulating
That's
around?
a good question. I think in their lifetime, they may take 3 or 4 trips through it. So it takes some amount of time.
But they're not constantly moving.
It's not in and out in 5 minutes. It's a significant amount of time.
Like months, right?
Like months of time.
Okay. All right. One of the things that you brought up, we've talked before this, about the significance of you using helium. Let's park on that for a second, because those of us who understand Fukushima and what happened there was an explosion. I think a lot of people think it was like a nuclear reaction that happened, but that's not what happened, right? It was the water molecules were getting split into free hydrogen, and that built up and exploded, right?
Yeah, so the typical nuclear fuel at reactors presently operating, when you have a loss of coolant, this case water. And even when you shut down the reaction, there's still heat being given off from the radionuclides that are still giving off some radiation. If you now lose the ability to move water through that and continue to cool that off, heat is going to build up. When the temperature of the fuel and the metal gets to a point where the metal starts reacting with water, then you get a zirconium metal water reaction, hydrogen is produced.
Sure.
And that buildup of hydrogen pressure inside a containment building so high, then you will essentially have a pressure explosion. It's not a radiation or nuclear explosion. It's literally just a mechanical pressure explosion.
Yeah.
But what it does is when it does that, then it opens up for release the radiation that you've got inside the reactor itself. That was the issue in a Fukushima, was the hydrogen buildup and the pressure and causing the explosion and release of the radiation.
And let's also make very clear that that was extremely atypical. There was a design where they were using diesel generators to pump the water around. Most nuclear plants are not located next to an enormous body of water that's susceptible to a tsunami. I just really want to get all of that preamble out there.
Yeah, so Fukushima, I mean, the bottom line was the tsunami took out all of that emergency power, the potential to recover. So the storm disconnected the plant from their electrical grid. So they didn't have the
Plants
ability,
need power.
right? So it was depowered. So they didn't have the chance to power their emergency equipment from the grid.
Yeah.
And so then when the tsunami took out also the diesel generators and the storage fuel tanks, that's when they lost their ability to, in an emergency situation. Since then, everyone around the planet has been working on other types of means if something like that were to happen. So again, by having problems and then learning from them, right? So we've even made nuclear plants even safer again, and because of what's happened and the adjustments that they've made since then. But that, you're right, it was very atypical, but it did happen.
So we're working on safety mitigation plans there. That's what we call the Gen 3 plus.
Gen 3 plus type of plan.
Right. And so what we're now working on is, of course, Gen 4. That's where you guys come in. And in this case, as many advanced reactor designs and everything, we're really trying to get away from this water contact, right? So we're going to try to avoid that altogether. And that's where the helium comes in. The helium is basically carrying the heat as opposed to water, right? That could possibly be split into hydrogen and all that sort of thing. So getting back to the fuel, I'm curious how these would work in a reactor. Would you retrofit an existing nuclear unit? Basically, what would be your plans for that?
Would you ever want to try to do that, retrofit a current one? A lot of things would play into that. If it was so difficult to license a new site somewhere, if a utility or someone decided we really want to have a nuclear plant operating, we do not want to continue with this standard metal fuel like a metal rod. We want to go to a TRISO type fuel. That's what we want to do. It's not just a matter of just changing out the fuel. There are other things you would have to retrofit into this reactor. So that whole fuel handling system, how do you store it? How are you going to move this? The safety systems, again, the helium, what we're using for that, if you want to go that route as opposed to water. There's so many things into play. It's going to probably be pretty difficult and pretty expensive if you were just to try to decide, I want to go from my standard fuel to a TRISO fuel in the plant that I already have.
I think the bottom line is that the assemblies, the configuration, those reactors are not broken enough for you to try to make that kind of retrofit.
But if you were going to decommission a plant anyway, so let's say we were going to cut out.
We'll take TMI, right?
Yeah, TMI. You have a site already, you have a containment, you have all of that. Maybe someone did decide, hey, we're going to cut this old reactor out, but let's keep all of this, and maybe at some point we do put a different type of design in there. I haven't really looked at that, but it may be something, since you've already done an environmental impact analysis of that area, you've already done a licensing for that area.
The containment.
Then it maybe makes sense to look at places like that to put other new, more advanced designs in at a later time. But just to say, I'm going to keep operating this plant, that would be a pretty difficult thing probably, unless you were deciding to decommission the other one.
I got you. You're also developing a small modular reactor, and I believe NuScale is currently As we're recording this, we're about a day removed from the announcement that NuScale finally got their design approval from the NRC.
Design certification. It's one of the steps in the process is to get design certification from the NRC. And they finished, I think, phase 6, they call it, the very final phase. So NuScale is the first of the small modular reactors to be design approved by the NRC.
So there's nothing left to do. They can basically...
Well, yeah, so you still now go through getting your client, start to do the construction.
But nothing's stopping them from going
from
out
a design
and commissioning
standpoint. They're not, they've got the go-ahead now to move forward.
And that's pretty amazing and really good for the whole industry. A couple of questions now with that bit of news. How does their design and your design compare?
Yeah, what's different? It's not significantly different in the power of each of the modules. There's a slightly less, so they need more modules to get to what's typical for a plant, let's say in the 300 to 400 megawatt electric size. They'll need more modules than we will. We might need 4, they might need 8 or 10, let's say. They're water cooled as opposed to ours being helium cooled or using helium. And then the fuel, again, we're a TRISO type of fuel where they're more of a typical light water reactor type of fuel. But the whole idea of much simpler safety related systems to try and reduce the safety significance of all the components that you have to build. Whenever you have a component that is involved with one of the safety systems, then it drastically increases the price to make it, because you just have to follow everything about how that was made, where the material came from, the quality requirements of all the material. The fewer safety systems you can have, the less expensive the plant's going to be.
Sure. So they've been through the gauntlet with NRC. I try to keep these episodes as evergreen as possible, but we are in the second half of 2020. Where does X Energy find themselves with NRC at this point?
So we have continuously been meeting with NRC through our whole design process. We're within probably about 12 months of starting the significant process of starting to provide them the materials for their reviews. So that's when you start to hand over the documents to the NRC for formal review, is once you get to final design.
So it's not a quick process.
It is not. It's 24 to 36 months once they have it in their hands. We're at the stage now where we need to get final requirements from our customers. What exactly do they want to have, right? Because you've got to make sure that's as close as possible.
Sure.
So that you don't have any one-offs, any things that the
NRC get turned around, right?
Yeah, well, again, some of the difficulties with the plants being built now in Georgia, the Vogel plants, again, is the review by NRC of the design. But once you're building it and you've got some differences, you've got to then, from a license standpoint, you've got to review a re-review of some areas because maybe it wasn't built exactly as what the paper design showed. That can really make it get expensive.
Look, I know the NRC is definitely no pushover. I got to talk to Ed McGinnis about a year and a half ago. It was a great conversation. And I think they reached out to me, and I think the big thing they wanted to push was SMRs. Yeah. And I would think that certainly DOE is super aggressive about SMRs and their potential. NRC, of course, isn't going to bend to however excited they are about it. They're going to go through the process. But considering that NuScale's now been through this process, and considering that the entire industry is really excited about SMRs, do you think that's going to help save you guys time going through your approval process?
Yeah, it will. And I think a lot of it's just because now they've done it. So there's not the angst of that first time through it. They've been through now a review process of something that's not the typical, right? So for 30 years, they've been looking at issues with light water reactors, boiling water and pressurized water reactors. And now these SMRs come along, and it will help too once you get one up and operating.
Yeah.
It's one thing to approve it now, again, to get your full comfort, let's see it operating and doing exactly what you say it's going to do. But you're right. I think it's going to help. At the end of the day, it's on us to show the NRC, though, that it's a safe design, it's a safe product.
And not to brag on you, but you have a lot of experience with this sort of thing. You worked for, was it Areva at the time, and now it's Framatome here?
Yeah.
Right?
So early in my career, it was Babcock and Wilcox, but then through Framatome.
Did you work on any of the constructions of any of them?
No, I came into the industry just after a lot of the plants were constructed. I was at Kansas State, and Wolf Creek was being constructed at the time. I actually got to walk through the piping while it was still under construction when I was in school. Most of them were just being completed as I was coming out of university.
I know. Darren, like me, is not 20 years old either, but that kind of gives you an idea about how much time has passed. And here we are finally building nuclear nuclear plants again.
Yeah.
I think it's really exciting to see this hopefully start to ramp back up in the next decade at least.
Yeah, with energy, I'm a big proponent of having a diverse portfolio of our generation. The nuclear plants are what are so good for having some level of base load that can operate all the time. So when we go turn our light switch on, it's going to come on whenever.
Yeah.
So in the next 10 to 15 years, a lot of it's going to drop off through economics or just age. And so what are we going to do to replace that? Because that's completely zero carbon.
Right. And I think people are going to learn very quickly that renewables, as much benefit as they provide, I think that everywhere that you've taken nuclear out of the equation, you take Germany and all these places, their carbon emissions have gone up. So X-Energy, of course, on their website, they talk about SMRs, you talk about full-size reactors. I think there's even a section about space, which I always think is so exciting. Yeah. Where do you really see the portfolio landing?
You know, we're all about clean energy, clean power, and looking at the global demand of energy over time. And part of that is for water. And how can we convert salt water to fresh water?
Sure.
Things like that. We chose this path of the advanced reactor design to be our part of that play for the global demand of power. The fuel that we've gone with, the TRISO X fuel, for space travel, NASA has now found that it's very desirable for space power, if you will. So heat on the moon or energy on the moon or on Mars or for the travel itself. This seems to be a fuel that they can utilize to do that. So they've become interested, and we're now working with NASA for providing this type of fuel to them. We're also looking at a micro-sized reactor for defense installations or for very remote power generation. And then of course we've got this group that's doing the commercial power plant size, and that's the XE100, which each unit's about 80 megawatt electric. Our first plant, we're looking at 4 of those, so it would be roughly a 320 megawatt electric plant.
Yeah.
That seems to be the ideal size for this small reactor market. Talking with the utilities, they need enough electricity from whatever they're doing to make it worth their while for all the effort you've got to make to get that type of electricity.
When it's nuclear power.
Right.
Yeah, we mentioned at the very beginning, X-Energy won an award to develop reactor designs back in 2019. It was a DOE award there. How does that fit into your overall, I guess, funding?
Yeah, so typically what they've seen is that they need to work with public companies or private companies to get these designs advanced. They're so expensive that a private company or a public company is probably not going to outlay that much design expense on their own. So the DOE has said, listen, we'd really like this to happen to keep the U.S. at the top of the field, if you will.
Right.
They think that the optimum way to do that is to work with commercial or public companies. So they put out what they call funding opportunities. So instead of just a national lab doing it, they're providing the funds to have public or private companies do it. And the intention is to set up commercial businesses to then build plants, provide the components for nuclear plants and all that. Again, with our XE100 design, we won a funding opportunity to help progress that. So.
Yeah, and so I wonder a lot about companies like yours, and I've talked to a couple of fusion companies, especially these companies that are going to take a little while before they're generating revenue, but they've got a very promising technology and everything. So it's kind of set up maybe like a tech company, right? You have Series 1 and all that sort of thing, and I guess you're meeting milestones. That's what keeps everybody happy.
Exactly.
Commercialization.
You lay out a plan that the department approves. These are the things that we're going to do under this funding opportunity.
But I assume you also had investors that aren't DOE.
You have some investors also. In our case, our company was a privately owned company, and that was the investor. That's where the other funds come from that matches.
As we're going through approval, I assume you're also trying to line up customers. So what about utilities? And one of the things I've talked about is, what are those conversations like, especially with utilities, where they would be conceivably the first to try this technology out? I know sometimes utilities are a little skittish about that.
Yes, it's really clear in today's economics. And this is what's so important about these funding opportunities from the Department of Energy. There's really no one right now that's going to show the economics of them building a plant and especially the first one, on their own. The economics are never going to play out. All the licensing costs, going through that first iteration of this, getting the supply chain set up and ready to go on this. So the Department of Energy sharing that cost for these first time through, that's a given that it's just going to happen that way.
Yeah.
So that's how you get the first one to happen. Once you've gone through the growing pains of the first time, then you will get more interest from utilities knowing that they've seen the first one built and knowing that you've got the supply chain now ready to go. So we have a U.S. utility lined up to go forward with us, and others who are talking to us about the 2028 to 2030 time frame for then maybe being the second or being the third of these types of plants to go forward.
You've been here for a little bit and you've seen a lot of stuff over the years. So what's the most exciting part for you about this role that you're in here? You're still kind of new to it. So.
Yeah, to me, I've been in the industry 36 years now. I have seen a lot of ups and downs. The exciting thing for me would be setting the stage for my kids and my grandkids. This plant, when it really does get built and start the wave of this next type of plant, to really set the stage for the next 100 years maybe for these types of plants to be built and support the world energy demand, if you will. That's a very exciting part of this.
Very cool. It's so crazy to think that I believe the whole concept of nuclear fission was first put on a chalkboard in the 20s or the 30s. They then did the Manhattan Project in the 40s, and the first functional nuclear plant was in service in the 50s. You know, so you're talking about 20 years between chalkboard to an actual plant, and you got to be thinking these days it takes about that long to build a plant, and here we are, we've been doing these things for over 50 years, so that's got to be frustrating, right? I mean, why are we not moving as fast now than we were when they started?
You know, that's a great question. A lot of it boils down to the public safety. We're just very careful with it because one of the initial uses of the power were weapons, right? That's what was the first visible use of it. That kind of set the stage in everyone's mind. Well, of course, we don't put concentrations of fuel in any of our commercial operations, but that's what set the stage for all of what we've done from a safety standpoint. So we are so super extra careful about everything we do and about any releases. So we take our time.
I can vouch for the fact that nuclear people are very safety minded. I did a nuclear facing transmission project one time, and the pre-job list was so extensive. I think I remember telling my managers, I don't want to do anything nuclear facing anymore. I am too ADD for that.
I joke with my friends. I said, you shouldn't think about not moving close to a nuclear plant. You should think the opposite, because all the water, everything is going to be cleaner around a nuclear plant than anywhere else because of how careful and how...
It would drive most people crazy to see the protocols that they do. I'm going to finish with a lightning round of your thoughts on different energy technologies, starting with natural gas.
Reduced carbon compared to burning coal.
Crude oil.
One of the resources of the U.S. We continue to try and make it cleaner and cleaner, but it's a resource we have, so we should continue to use it as much as it's feasible.
Nuclear, you guys.
Yeah, it's got to be a part of the portfolio going forward to have clean energy.
Coal.
In the U.S., one of our resources that we've had, it was really what started our electrical industry. It's why we have the standard of living we have today. Let's just continue to look for cleaner and cleaner ways to use it, but I think we should continue to use it as we can.
Wind.
I grew up in Central Plains states where it's feasible to use. Let's use it as much as we can, but we've got to continue to find ways to store it. Battery technology or energy storage systems to better utilize it.
Solar.
The same concept as the wind, where it's possible, where it's used. It's part of a diverse portfolio. Let's just continue to develop the power storage system so that it can be more efficiently used.
Biofuels.
It's pretty expensive and you're burning something again, so I don't know that it's the absolute way to go forward, but it can be a part of a diverse portfolio if it makes sense in certain parts of the country.
Hydroelectric.
That's a regional type of energy. Where we have it, it continues to be very clean from a carbon standpoint. I think we should use it where we can.
Geothermal.
It's been difficult. It's not a widely used type of energy, but can be used for local heating more efficiently than some of the other ways.
Energy storage.
That's the key. As my kids were growing up, I said, if you want to be Bill Gates rich, then develop a way to efficiently store energy. That is really the key going forward. How can we store renewable energy so you can then go back later and utilize some of that power?
Electric vehicles.
We absolutely should continue to move forward with it. I think most infrastructures around the world have not been moving fast enough to enable electric vehicles. When you think about we've powered vehicles by gasoline for so long, that infrastructure of gasoline stations and all that, we need to be moving quickly to have electric recharge stations for our vehicles.
Yeah, energy efficiency.
Reducing the requirements that we need helps contain how much coal we're burning or how much whatever we're doing from an energy standpoint. That's got to be a continued part. Now, at a point, you kind of lose the gain on the amount of money you spend on it. I mean, at some point, you've got to use energy. I don't know if we can make significant strides going forward, but it's always something you need to look at.
You bet. And then finally, fusion power.
Yeah, we understand the technology of the fusion. This is really all about materials research in my mind. How do you contain the reaction? That's what that science is all about.
All right, Darren Gale, X-Energy, thank you so much for your time.
Jay, have a great day. Thank you.
That was Darren Gale, Vice President of Commercial Operations for X-Energy, a nuclear reactor and fuel development company recorded at the EnergyCast Global Studios in Charlotte, North Carolina. I want to thank Darren for his time, as well as Robert Sislow at X-Energy and listener Abe Kaplan for getting this on my radar. You can find plenty of pictures on energy-cast.com, as well as on Instagram and Parler at Host Energy and Twitter at Host Energy Cast. All guests are sent the raw and completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 93. Be sure to join us next week when we discuss the energy challenges currently facing the Golden State. Until then, I'm Jay Downhauer. We'll see you next time.